In the heart of Vienna, on August 12, 1887, a child was born who would fundamentally change how we understand reality itself. Erwin Rudolf Joseph Alexander Schrödinger entered a world of intellectual privilege. The only child of Rudolf Schrödinger, a botanist and linoleum manufacturer, and Georgian Emilia Brenda, the daughter of a chemistry professor. But this wasn't just any privileged upbringing. This was Vienna at the height of its cultural and scientific renaissance, a city buzzing with the ideas of Freud, Mahler, and Klimt. The young Erwin grew up in a home where science was dinner conversation and curiosity was currency. From the beginning, Schrödinger was different. While other children played in the streets, he was equally comfortable in 3 languages, German, English, and French, all spoken fluently in his household. His father, a polymath in his own right, cultivated in Erwin not just knowledge, but a love of learning itself. The family would spend hours discussing philosophy, science, and art, treating the young boy not as a child to be seen and not heard, but as an intellectual equal in training. This early immersion in multidisciplinary thinking would later become Schrödinger's trademark. He would never be just a physicist, but a philosopher of nature, someone who saw connections where others saw boundaries. His formal education began at the Akademisches Gymnasium in Vienna, where he excelled at everything: mathematics, physics, classical languages, literature. His teachers noticed something unusual. While most students specialized early, Schrödinger refused to choose. He devoured Greek poetry with the same passion he applied to differential equations. This wasn't scattered interest, it was an integrated worldview forming. He believed deeply, even as a teenager, that separating the sciences from the humanities was an artificial and damaging distinction. This holistic approach would later permeate his scientific work, leading him to insights that more narrowly focused minds might miss. In 1906, at age 19, Schrödinger enrolled at the University of Vienna, where he studied under some of the giants of physics, Franz Seraphin Exner and Friedrich Haesnerl, the latter being a student of Ludwig Boltzmann, whose work on statistical mechanics would profoundly influence Schrödinger's thinking. The University of Vienna at this time was a crucible of ideas. Schrödinger attended lectures not just in physics, but in philosophy, attending sessions where the nature of knowledge itself was debated. He read Arthur Schopenhauer obsessively, finding in the philosophers works a resonance with his growing sense that reality might be fundamentally different from how it appears to our senses. This philosophical bent would never leave him. Even his greatest scientific papers would be infused with questions about the nature of reality, consciousness, and existence. Schrödinger completed his doctorate in 1910 with a dissertation on atmospheric conductivity. But this was hardly groundbreaking work. He was still finding his footing, still searching for the problem that would define him. Then came World War I, and with it, a brutal interruption. In 1914, Schrödinger was drafted into the Austro-Hungarian army, serving as an artillery officer on the Italian front. Imagine the surreal contrast: this deeply intellectual, gentle soul, more comfortable with equations than with weapons, now commanding a fortress battery in the mountains. Yet even here, in the mud and horror of war, Schrödinger found time to read physics papers and think about science. He would later say the war years, paradoxically, gave him time to think deeply about fundamental questions without the distractions of academic politics. When he returned from the war in 1918, the world had changed, and so had he. The Austro-Hungarian Empire had collapsed. Vienna was impoverished, food was scarce, and the intellectual world that had nurtured him was shattered. But Schrödinger pressed on, taking a series of positions, assistant positions in Vienna, then Jena, then Stuttgart, then Breslau, moving around like an academic nomad, never quite finding his home. During this period, he married Annemarie Bertel in 1920, beginning a relationship that would be as unconventional as everything else about his life. They had an open marriage, unusual for the time but consistent with Schrödinger's rejection of conventional boundaries. He would have multiple affairs throughout his life, several producing children, and Annemarie would have her own relationships. It was messy, human, and completely at odds with the stereotype of the buttoned-up scientist. Professionally, these were Schrödinger's wilderness years. He worked on color theory, on the theory of specific heats, on radioactivity, solid work, but nothing revolutionary. He was talented, clearly brilliant, but not yet touched by genius. Other physicists were making the breakthroughs. In 1913, Niels Bohr had proposed his model of the atom. In 1923, Louis de Broglie suggested that particles might have wave properties. The quantum revolution was happening, and Schrödinger was, at best, a spectator. He was now in his mid-30s, an age by which most great physicists have already made their mark. Einstein had published special relativity at 26, general relativity at 36. Heisenberg would develop matrix mechanics at 23. Was Schrödinger to be merely a footnote, a competent physicist who never quite achieved greatness? Then, in 1921, his luck changed. He secured a position at the University of Zurich, finally achieving some stability. Zurich was a scientific powerhouse. Einstein had taught there, and it remained a hub of theoretical physics. Here, Schrödinger could focus, could engage with the best minds, could finally have the resources and time to pursue the big questions. He was 34 years old. The stage was set, though he didn't know it yet, for the most productive few months of his entire life, a period that would change physics forever. The year 1925 was pivotal for quantum mechanics. That summer, a 23-year-old Werner Heisenberg, recovering from hay fever on the barren island of Helgoland, developed matrix mechanics, a mathematical framework for quantum phenomena that was powerful but abstract, filled with non-commuting matrices that even most physicists found bewildering. It worked, but it was ugly, or so Schrödinger thought when he first encountered it. He found the mathematics discouraging, if not repulsive. This wasn't just aesthetic preference. Schrödinger believed deeply that the laws of physics should be beautiful, that truth and beauty were somehow connected. Matrix mechanics felt wrong to him, like a correct answer obtained through the wrong method. In late 1925, Schrödinger attended a seminar where a colleague discussed de Broglie's idea that particles might behave like waves. Something clicked. If electrons are waves, Schrödinger reasoned, there must be a wave equation that describes them, just as there are wave equations for light or sound. But what would such an equation look like? This question consumed him. In December 1925, Schrödinger did something unusual. He left his wife in Zurich and retreated to a villa in the Swiss Alps, to the resort town of Arosa, bringing with him an old girlfriend whose identity remains uncertain to this day. There, in a passionate mixture of intellectual and romantic intensity, Schrödinger worked with feverish concentration. What happened in those alpine weeks is the stuff of scientific legend. Working with extraordinary speed and clarity, Schrödinger derived his wave equation, the equation that now bears his name. The Schrödinger equation describes how the quantum state of a physical system changes over time, representing particles as wave functions that evolve according to precise mathematical laws. It was elegant, it was beautiful, and it worked. When Schrödinger applied his equation to the hydrogen atom, out popped the correct energy levels, the same ones that Bohr had derived through a more ad hoc approach, the same ones that Heisenberg's matrix mechanics predicted. But Schrödinger's method was different. It used the familiar mathematics of wave equations, calculus that any physicist could understand. Where Heisenberg had offered abstraction, Schrödinger offered intuition. Between January and June of 1926, Schrödinger published 6 papers in rapid succession, developing his wave mechanics in extraordinary detail. He showed how his approach and Heisenberg's matrix mechanics were mathematically equivalent, 2 different ways of saying the same thing. But more than that, he provided the tools that would allow quantum mechanics to be applied to real problems. The Schrödinger equation became the workhorse of quantum theory, the equation that chemistry students and physics students would learn to solve, the foundation upon which all of modern quantum mechanics would be built. At age 38, after years in the wilderness, Schrödinger had finally achieved his masterwork. He was no longer a promising physicist. He was one of the founders of quantum theory itself. The response was immediate and overwhelming. Max Planck, the father of quantum theory, invited him to Berlin as his successor. Niels Bohr engaged him in intense debates about the interpretation of quantum mechanics. Einstein, whom Schrödinger revered, praised his work while sharing Schrödinger's discomfort with some of quantum theory's implications. In 1926, Schrödinger moved to Berlin, joining the most prestigious physics department in the world. He had arrived, but Schrödinger's relationship with quantum mechanics was complicated, even tortured. He had created the mathematical framework, but he increasingly hated what it seemed to imply about reality. The Copenhagen interpretation, championed by Bohr and Heisenberg, suggested that quantum systems exist in superpositions of states until measured, that an electron doesn't have a definite position until you look at it, that reality itself is fundamentally probabilistic and observer-dependent. This bothered Schrödinger deeply. He had hoped his wave equation would restore determinism to physics, would show that quantum particles were just waves, continuous and concrete. Instead, his equation seemed to support the opposite conclusion. The debate came to a head in 1935, 9 years after his great papers, when Schrödinger published an essay titled The Present Situation in Quantum Mechanics. In it, he introduced what would become his most famous contribution to popular culture, though it was meant as a criticism, not a celebration, of quantum theory. He asked readers to imagine a cat in a sealed box with a diabolical device: a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the Geiger counter triggers, the hammer breaks the vial, and the cat dies. But according to quantum mechanics, until we open the box and observe, the atom exists in a superposition of decayed and not decayed states. Which means, by the logic of quantum theory, the cat must be simultaneously alive and dead until we look. Schrödinger thought this was absurd, and that was precisely his point. He wasn't proposing that cats really could be both alive and dead. He was arguing that quantum mechanics, pushed to its logical extreme, leads to ridiculous conclusions, therefore something must be wrong with our understanding. The cat was a reductio ad absurdum, a way of showing that the Copenhagen interpretation couldn't be right. Cats are either alive or dead, not both. Reality, Schrödinger insisted, must exist independently of observation. It is fair to state, he wrote, that we are not experimenting with single particles, any more than we can raise ichthyosauria in the zoo. The irony is that Schrödinger's cat, meant as a critique, became quantum mechanics' most famous illustration. It captured the public imagination precisely because it was so weird, so counterintuitive. Today, the thought experiment adorns t-shirts, appears in cartoons, and serves as a gateway to quantum theory for millions of people who have never solved a differential equation. But for Schrödinger himself, it represented failure. His failure to convince his colleagues that quantum mechanics, for all its predictive success, might be missing something fundamental about the nature of reality. In the same 1935 paper, Schrödinger introduced another concept that would prove even more important: entanglement, or, as he called it, Verschränkung, literally entanglement in German. He described how quantum mechanics allows particles to become correlated in ways that seem to defy common sense, so that measuring one particle instantly affects the other, regardless of the distance separating them. Einstein would call this spooky action at a distance, and like Schrödinger, saw it as evidence that quantum mechanics was incomplete. Today, entanglement is recognized as one of the most profound features of quantum reality, the basis for emerging technologies like quantum computing and quantum cryptography. But in 1935, for Schrödinger and Einstein, it was a problem, not a feature, evidence that something was deeply wrong with the theory. The 1930s brought darkness to Europe, and Schrödinger's comfortable position in Berlin became untenable. Though not Jewish himself, Schrödinger was horrified by the Nazi regime. In 1933, when Hitler came to power, Schrödinger made his opposition clear. He publicly denounced the dismissal of Jewish colleagues and refused to give the Nazi salute. This was dangerous. His colleagues warned him, but Schrödinger's intellectual integrity would not allow silence. In the same year, he was awarded the Nobel Prize in Physics, sharing it with Paul Dirac, for the discovery of new productive forms of atomic theory, the wave equation that had revolutionized physics. But even a Nobel Prize couldn't protect him. Schrödinger knew he had to leave Germany. He accepted a position at Oxford, fleeing Berlin with his wife and also with Hilda March, the wife of a colleague with whom he had fallen in love and who was pregnant with his child. This arrangement scandalized Oxford society. Imagine a Nobel laureate arriving with his wife and his pregnant girlfriend. It was too much for conservative British academia. Schrödinger was brilliant, but he was also a problem. He stayed at Oxford for a few years but never quite fit in. He felt isolated, foreign, uncomfortable. In 1936, he accepted a position in Graz, Austria, returning to his homeland. But this too would be short-lived. In 1938, Nazi Germany annexed Austria in the Anschluss, and Schrödinger found himself once again under Nazi rule. Worse, he had been too public in his opposition. He was dismissed from his position and briefly faced the possibility of arrest. He managed to escape with his wife to Italy, then to Switzerland, and finally to Dublin, Ireland, where the government, at the urging of Irish statesman Eamon de Valera, himself a mathematician, offered him sanctuary and a position at the newly created Dublin Institute for Advanced Studies. Ireland became Schrödinger's home for the next 17 years, from 1939 to 1956. These were productive years, though he never again achieved the revolutionary breakthroughs of 1926. He worked on unified field theory, trying to unify gravity and electromagnetism in the way Einstein had attempted, an effort that, like Einstein's, ultimately proved unsuccessful. But he also turned increasingly to philosophical questions, to the big-picture issues that had always fascinated him. In 1944, he published a slim volume titled What is Life? That would have an impact far beyond physics. What is Life? Was Schrödinger's attempt to apply physical principles to biology. In it, he asked how living organisms maintain order in a universe governed by the second law of thermodynamics, which dictates that disorder, entropy, always increases. He proposed that life feeds on negative entropy, extracting order from the environment. More importantly, he speculated about the molecular basis of heredity, suggesting that genetic information must be stored in some kind of aperiodic crystal, a stable molecule with a complex structure that could encode information. This was remarkably prescient. 9 years later, Watson and Crick would discover the structure of DNA, the aperiodic crystal that carries the genetic code. Both Watson and Crick cited What is Life? As an inspiration. Schrödinger, the physicist who had helped birth quantum mechanics, had now pointed biology toward its greatest discovery. In Dublin, Schrödinger also wrote extensively on philosophy, publishing Mind and Matter in 1958, exploring consciousness, the nature of the self, and the relationship between observer and observed, questions that his work in quantum mechanics had made urgent. He drew on Eastern philosophy, particularly Vedanta, finding in Hindu and Buddhist thought a conception of consciousness that resonated with his quantum mechanical insights about the role of the observer. He suggested that individual consciousness might be aspects of a single universal consciousness, that the separation between observer and observed, between self and world, might be illusory. These were radical ideas, more philosophy than physics, but for Schrödinger, there was never a firm boundary between the two. In 1956, at age 68, Schrödinger finally returned to Vienna, the city of his birth, accepting a chair in physics at the university where he had studied half a century earlier. It was a homecoming, a closing of the circle, but his health was declining. He suffered from tuberculosis, and his energy was no longer what it had been. He continued to work, to lecture, to think about the problems that had occupied him for decades, the interpretation of quantum mechanics, the nature of consciousness, the unity of knowledge. But the great breakthroughs were behind him. Erwin Schödinger died on January 4, 1961, in Vienna, at age 73. He was buried in the village of Alpbach in the Austrian Alps, a place he had loved for its beauty and tranquility. His gravestone bears the Schrödinger equation, the wave equation that describes quantum systems, the equation that represents his greatest achievement, inscribed in mathematical symbols for eternity. It is a fitting memorial for a man who believed that mathematics was the language of reality. So what is Schrödinger's legacy? On one level, it's straightforward. The Schrödinger equation is one of the most important equations in physics, foundational to all of quantum mechanics, chemistry, and materials science. Every time a physicist calculates the behavior of atoms, every time a chemist predicts molecular structure, every time an engineer designs a semiconductor, they are using Schrödinger's equation. It is the tool that made the modern world possible. Transistors, lasers, MRI machines, solar panels, all depend on quantum mechanics, which depends on Schrödinger's work. In this sense, his impact is immeasurable, but Schrödinger's legacy goes deeper. He was one of the last true polymaths in physics, someone who refused to separate science from philosophy, physics from biology, reason from emotion. He believed that the great questions were all connected. What is matter? What is life? What is consciousness? And that narrow specialization, however necessary for technical progress, misses something essential. In an age of increasing compartmentalization, where physicists don't talk to biologists who don't talk to philosophers, Schrödinger's holistic vision feels both antiquated and urgently needed. His personal life was messy, unconventional, at times scandalous. He had affairs, he fathered children outside his marriage, he rejected social conventions. But this wasn't mere libertinism, it was of a piece with his intellectual approach. Just as he refused to accept arbitrary boundaries in thought, he refused to accept arbitrary boundaries in life. He lived according to his own principles, seeking authenticity even when it cost him professionally and socially. In his personal life, as in his physics, Schrödinger was someone who insisted on going to the foundations, questioning assumptions, refusing easy answers. Perhaps most importantly, Schrödinger never stopped wrestling with the implications of quantum mechanics. While many of his colleagues moved on, applying quantum theory to new problems without worrying too much about what it all meant, Schrödinger couldn't let go of the interpretive questions. He died still uncertain about what his equation really described, still uncomfortable with the probabilistic, observer-dependent world that quantum mechanics seemed to reveal. Some see this as a failure. He created the theory but never accepted it. But maybe it's the opposite. Maybe his persistent discomfort reflected a deeper wisdom, an unwillingness to pretend we understand more than we do. The measurement problem, the role of the observer, the relationship between quantum and classical reality. These questions remain unresolved today, hotly debated by physicists and philosophers. Schrödinger's cat is still both alive and dead, in a sense, because we still don't fully understand what quantum mechanics is telling us about reality. In the end, Erwin Schödinger was a scientist who never stopped being human, passionate, curious, flawed, searching. He gave us the tools to describe the quantum world with unprecedented precision, but he also never stopped asking what it all means. He was a physicist who read Schopenhauer, a scientist who meditated on consciousness, a rationalist who sought mystical insight. He was, in short, someone who understood that knowledge without wisdom is incomplete, that equations, however beautiful, are not the end of the story. His life reminds us that science at its best is not just a technical enterprise, but a human one, driven by wonder, animated by deep questions about who we are and what kind of universe we inhabit. The equations endure, carved in stone on his grave. But so do the questions, alive in every physicist who looks at quantum mechanics and wonders, as Schrödinger did until his last days, what it's really trying to tell us about the nature of existence itself.